it's not conducting, and it is not is isolating either. And this is between. As the name suggests, semi means partially something. You guys have heard the Silicon Valley, right? Silicon Valley is a silicon that is talk about the silicon. That is silicon is the building block of this is the computer industry. And so here are today's objectives, and we want to learn the types of diodes. Last time I introduced the diodes to you guys, and we know the diode only allows the current flow in one direction, and from the we call this is forward bias. The reverse bias, and just theoretically we just think so the current equals 0, but practically the current is very tiny. And we'll talk about other diodes. There are several variations, and also their basic behaviors, how they behave. And then we learn the behavior of bipolar is a junction transistor, and bipolar the junction transistor, and BGT, that is talk about NPN and PNP, the transistors. And then we learn another very effective one. Is also called transistor. This is called metal oxide semiconductor field effect transistor. It's very long name. The acronym is MOSFET. And MOSFET and how to use it, and how the MOSFET is different from BGT. I'm going to ask you guys. Okay, so the transistor BGT appeared a little bit earlier, and then as the technology evolved and people introduced the MOSFET. MOSFET is better in some aspects when compared with the BGT. So this is our today's objectives. So I first introduce the semiconductor. As the name suggests, and semiconductor, and it is a bunch of materials that make up these devices. And here we call devices. Devices here means some special material that we use for some special application. Okay, device here. So whenever when you work in the federal government, is a lab, and you will hear people talking about devices. When you hear in that context, when you hear device, it means that it is a special material to satisfy some special needs. Can you understand, guys? The device is here. Device in material science, device is kind of different from the device we are referring to in our mechanical engineering. But so device, we call device. Use this device exhibit neither the low resistance typical of metal and other conductor. We know metals they are conducting. These are electrical conducting and also heat conducting, and other conductors, nor the very high resistance associated with isolators. So isolators means, for example, the polymers, the ceramics, and they are theoretically we call them and they are isolators. Okay, because for ceramic. For some ceramic, if you apply the cathode and anode on two ends, usually there is no current. So that's the reason for ceramics, or sometimes we call isolator. For metals or other kind of materials, they call this is the conductor. And don't get me wrong, some special ceramics, they are also electrical conducting. When I say ceramics usually are isolators, I'm talking about the commonly seen the ceramics. Okay? And some special ceramics, they are electrically conducting just like metal. So this is one of my research area. I'm focusing on that one. So you can see conductor is one extreme, isolator is another extreme. In the middle is a semiconductor. So here I want to tell you guys, I want you guys to remember what are the three commonly used semiconductors: silicon, germanium, and helium. Right? We have three different categories. Silicon is commonly used one, and it's very easy to remember because we know in California we have Silicon Valley, right? And germanium and helium. So these are three basic building blocks for the computer industries. And in this is the since 60 something or 70 something. So you can see, okay. So the usefulness increases dramatically when very small amount of specific materials, and for example, boron and phosphorus are added to the pure semiconductor. So theoretically speaking, pure semiconductor is useless. Pure semiconductor is useless. When this guy becomes useful, and when you add some doping materials, doping elements, for example, boron and phosphorus, the conductivity of the resulting material can be modified by applied voltages. As a result, combining regions or layers that are seeded here is also called doping. Doping means you are adding something special and to enhance the performance of this whole material. With different materials, many different kinds of devices with very useful properties can be made. So for this paragraph, and my bottom line is that you know what are commonly two doping elements, boron and phosphorus. If you add boron to this material, and you get the N, you get N semiconductor. If you add phosphorus, you get P, this semiconductor. So last time in the previous sessions, I mentioned NPN, PNP, right? That is why we call N, why we call P. So semiconductors are the basic building blocks for all electronic devices. And then we have this integrated circuit where many semiconductors and resistors or capacitors are combined into one single device. This is called integrated circuit. Any question regarding this slide, guys? So this is a fundamental knowledge about semiconductor. Your name is
Ricky.
Ricky. Yeah. Okay.
When you add specific materials, is that combining them with the semiconductors like an alloy, or is it like layering them?
That's a good question. So you just I don't know. You just put something there. How to do this layer by layer, or just thoroughly allowing them together? That is another question. Yeah, a good question. Okay, that's a good question. So what I'm understanding is they just put a tiny amount of things in one specific area. Aiden, right?
Yes.
Aiden.
Just to be clear, you said when you add boron, it becomes the N semiconductor, or is that the P semiconductor?
When you add boron to silicon, you get N semiconductor.
Okay, so when you add phosphorus, it's the P semiconductor?
Yeah.
Okay.
Okay. So based on these slides, on the three commonly used semiconductor, silicon, germanium, and gallium, and two commonly used doping elements are boron and phosphorus, right? You can see without the silicon, germanium, gallium, and without boron and phosphorus, and we are still living in the Stone Age. I'm kidding. With no computers, we don't have computers. Can you imagine? If we do not use computers for 24 hours, what will happen to our society?
The world end.
Huh?
The world will end.
What?
The world will end.
World War?
No, like the world will like end. Like we
No end, but we are going back to the Stone Age. I'm kidding, okay? Silicon Age, not the Silicon Age. So you can see, okay? So pure silicon is not of much use. It can become useful only when it is doped by adding small amounts of other items onto the crystal structure. The most common dopants are boron and phosphorus. And this is what I told you guys. So N type, okay, I just correct what I said. N type is you, and this is phosphorus. Right, so guys, be very careful. N type, you add phosphorus, and for P type, and you add silicon. So don't get it wrong. So N type, what is N type semiconductor? So we know, guys, the silicon, how many covalence electrons the silicon has, and based on what you have learned in chemistry or in physics, Kevin?
What?
How many covalence electrons and the silicon has? Covalence electrons means the electrons in the outermost layer of this atom.
Honestly, it's been a while. I don't remember.
4, right?
Oh, it's 4?
Yeah.
Okay.
So that's the reason 4. It can. So it is if it is very small. If it's 1, it's a very chemical reactive. If this is a covalence electron number equals 7, it is also the chemically reactive. You guys still remember that? But in the middle, 4. In the middle, 4. It is not very easy for me to get the 4 electrons from other place to get 8, or it is not easy for me to lose these 4 electrons, and for me to get 0 covalence electrons. So that's the reason. And for this kind of material, which have 4 covalence electrons, they are very stable. Understand? So if some elements they have 8 covalence electrons, they are very inert. Right, guys? We have inert the gases. Do you remember what are the commonly used is inert gases?
Argon.
Argon is one. So whenever we want to maintain this is chemical stability, and when we alloy some materials, and we usually conduct these experiments in an argon environment. Okay, so why argon is chemically stable? Because this guy's covalence electron is 8. 8 means that no matter I don't want to do any exchange of electron exchange to any other materials, any other electrons. So this is for here, okay? The phosphorus, these guys have 5. These guys have 5 covalence. So silicon has 4, and 4 of the valence electrons from the phosphorus will participate in covalent bonds with the adjacent silicon atoms. So here is the 4, and so this is valence. So this is 5. This is have 5 valence electrons. This is 4 plus the 4 out of 5, and they will form a very stable covalence bond. This is a covalent bond, and then but the phosphorus will have free electrons, and so these are free electrons. One of the electrons from the phosphorus will be more loosely bonded to the crystal. So this guy can move whenever you have externally applied voltage. So externally applied voltage can cause this electron to migrate through the crystal lattice, resulting in a current flow. And even though when we talk about the current flow, it is the opposite direction of the electron movement. You understand, guys? So here you can see the 4 valence electrons from silicon, and will come together with the 4 valence electrons from the phosphorus, but there is 1 free phosphorus electrons, and this guy can move when you apply the externally external is the voltage. So then this will can have a current flow. So this is called N-type semiconductor. Any questions regarding this slide? No question? Then we just look for comparison. Here is a p-type. And p-type is a boron. The boron here, so this guy has 3 these valence electrons, and 4, this is 3. And the 3 valence electrons from the boron will participate in covalent bonds with the 3 adjacent silicon atoms, leaving a hole with the 4th adjacent silicon atom. So externally applied voltage can cause one of the electrons from adjacent atom to move to this hole. So this is hole. Okay. So in doing so, this electron has left another hole where it is used to reside, and in this way the hole traverses the crystal lattice under the influence of externally applied voltage. And even the hole has no charge of its own, it is considered to be a positive charge carrier. You understand, right? Now this time, you can see the hole microscopically. You can see the hole is changing. The hole is moving. It's not hole is not moving, okay? And visually, the hole is moving, but it is not moving. You can just see the new hole because the electron that residing there previously moved to the previous hole. You can just visually you can just see the hole is moving. But here the hole here is treated as a positive charge carrier because it is in the opposite direction of the movement of the electrons. Questions? Boron and phosphorus. Boron and phosphorus. Now this is diode. Last time I showed you this the diode values. As I said, so this figure is a figure. I got this figure from this textbook, and so this one is not right. Okay, so this one this is the cathode. So this is anode. So here you can see we call forward bias, and this is reverse bias. And forward bias means that we have a current, and we will have a current that goes through the diode. And the reverse bias theoretically, and we call no current, even though practically it's a small, very, very tiny amount. You can see the unit nanoampere, 10 power minus 9. It's very, very small. But so this is, and we know this slide. So this is a VI characteristic for a diode on forward voltage and leakage current and reverse breakdown of voltage VR. So we talked about this one already. Keep in mind, if you want this diode to carry and to allow the current to flow through, and you need to apply this is the voltage using the forward bias. So this is the diode. So this magnitude of this is voltage depend on the material used in the construction of diode. And you can see for gallium, and this is the silicon, and they have different voltage. You have different VI the voltage. So VI characteristic for germanium, and this is germanium and the silicon diodes. So we said we know silicon, germanium, and gallium. We have 3 different semiconductors. So this is diode. This diode shows that one diode, the transitions from being forward biased to being reverse biased. It is not capable of instantly eliminating the current flow. Rather, a small but finite amount of time is needed. So this is forward bias. You have current here. Now, if you want to switch the this is the polarity. If you switch the polarity of the power, and theoretically it should go from this is the distant value and to 0. However, it is no. In the next time, go this way, then come back 0. So this is a finite amount of time. So this is understandable. Okay, this is practically you need some time to adjust this current flow. So Zener diode, Zener, we call this Zener, right? Zener. Last time I told you guys what is one of the beautiful property of Zener, guys. Zener is a specialized diode. What is a beautiful property of that Zener we can use, Eden?
When you reverse bias it, it has a voltage, right?
Yeah. Okay, that's good. And for this Zener, if we reverse, if we apply load reverse in the reverse bias, and we will have a stable voltage. So this is a very beautiful. This is a very beautiful property. If you want to stabilize the voltage somewhere in your circuit, and you can put a Zener diode there, okay? And then you can see the Zener diode will be almost constant. This is a very, very beautiful one. When I was a master student, that's many years ago. I just designed the board, and then I just add all these elements in the board. And when I want to stabilize the voltage there, and I use the diode. I use this Zener. So this Zener, different Zener, they have different constant. This is the voltage value when it is reversely biased. Questions so far? So this is very beautiful property for Zener.
So current can it flow in both directions then?
No, current will not go through deep direction. For both direction is also small, but the voltage is maintained. Right? When you reversely bias, this is reverse bias, or this is reverse bias, and you will have a very, very tiny, almost negligible is a current, but the voltage is stabilized. I'm talking about the voltage. Here, I'm not talking about the current. Okay. The voltage is still very low. You can see nano, and then nano is very, very small. You can see here. You can see this here. This is this is we put a Zener here. So the node here is a ground. Then the voltage on the node A and will be stabilized. Right? Because
Sorry, by stabilized you mean like a constant voltage value?
yeah, constant.
So what's the alternative with a standard diode?
A standard diode, that means this is no, this is not this is a constant.
Okay.
It's not a constant. You can see here, this is zero. The voltage here is theoretically zero, right? This is zero. I put this one anyway. This one will be higher than zero. So this is a fully reversed. Fully reversed means that I can see, make sure the diode at this node A, we will have stabilized the voltage. And how big it is, and we need to check this is the Zener you are using, and on the data sheet of from the vendor, and this value will be given. Questions so far? No question? And then we have a look at another diode, and it's called a light emitting diode. And so this one is we are very familiar with these things in our daily life, right? When the Thanksgiving approaches and this Christmas approaches, when we decorate our houses, what kind of things we are using? We use LEDs. You guys remember? Or what kind of decoration things you are using? I use LED to decorate my house. Right? What is LED? LED means that if you put some voltage there and different LED, and you will have different colors. Right? Right, guys? Okay, so you can see the forward voltage, based on the forward voltage, and you have the current, and you will have different. This is the color, different color of this is LED, and then this is very beautiful, very colorful the decoration. So green color, blue color, yellow, and red. So this is very, very beautiful. Questions so far? So keep in mind, for this LED, the current, the voltage is the cause. The light is with infrared. Why I tell this? Because next slide, we are talking about another the diode which has a reverse. This is the cause and effect reversed. So question so far? For this one, if we have voltage, we have current, and then we have color. No, sorry. We have light, colorful light, colorful light. Right? The color is means light. Light come into our mind. So question so far, guys? This is for gallium. Now look at this one. Okay, so this is a photodiode. A photodiode is totally different. A photodiode means that if I have a photo, I have current. Photo here is a course, current is effect. You understand that? So this is kind of confusing, but I want you guys to know. For this is a photocurrent diode means that if I have a photo, and put this is the diode in the photo, in kind of photo, and I can have current. Different photo will result in different magnitude of current. For the previous one, LED, different current voltage can result in different colorful light. When you see the light, then you know the color. Okay? You understand, guys? Okay, you can see here, forward biased, this reverse biased, no light is very, very small. If you have light, is increasing light intensity, and you will have higher. So this is the current level. So I might ask you on how these two guys are different from each other. LED and photodiodes. And then we talk about this is a bipolar junction transistor. We have NPN and PNP. Now, from now on, we call them the bipolar because we have a MOSFET there. A MOSFET is another category of transistor. So this picture we know this picture already, right? So we know this one. And so with NPN, you can have 3 layers. This is the PNP means the P semiconductor layer. So N. P is a semiconductor layer. So this is a sandwiched this way. And for this one, we also have 3 layers, but I put this is the N semiconductor in the middle. And on our side, I have 2 P conductors. So these 3 guys are sandwiched this way. So this is kind of different. The different sandwich mechanism and will result in different this is a function. Look at it here for this one, NPN. And we have a base emitter. You can emitter. What emitter means just emit something. And the collector is a collector, and there's a current going through from this collector. So in the PNP, the base is same, but the emitter and the collector changes. The role change. So this is emitter, the position change. This is emitter, still the emitter. Whenever we talk about emitter, there is arrow there. Arrow, whenever you see the arrow, the terminal, that means the emitter terminal. So this is the C, the collector, PNP. So these 2 guys. So here is the chart. When this is the transistor is turned on. Turn on here means that it allows the current to flow. Right, guys? You need to be very careful, okay? When we say turn on means that there is current. Turn off, cut off the current. So you can see, okay, for NPN and PNP. So how it works, I told you guys. So for this one, for both of these 2 cases, we compare the voltage difference between the base terminal and the emitter terminal. Here is also emitter terminal. If the voltage difference between these 2 terminals is higher than the threshold value, and for this case, it is 0.6 volts. If this is inequality is higher or equal to, if this is inequality and equal equation is satisfied, and we will have current. Otherwise, no current. Theoretically, no current, but it still have very, very tiny, very, very small amount of current. But we just treat this kind of current as no current. Question so far? So, in the following circuits, and how can we interpret how this circuit works or not? And we use this principle. Okay. Whenever we for the basement for this base terminal and what condition when we apply what kind of signal, what kind of voltage on this base terminal, what will happen in the following circuit, and we will follow this principle. Okay, guys, questions so far? No questions? One more time, and we check the voltage difference between the base terminal and the emitter terminal, and this is the same for both of these two cases, NPN and PNP. You got here. So very the simple one. So here is a ground. Ground means I just treat this one as a 0. And VIN, this is the input voltage. If this input voltage is very low, how low? As long as the voltage difference between these two guys is less than the threshold value, for this case 0.6 volts, no current. Right? However, if I increase the voltage value, and then so the voltage difference between this terminal and this terminal exceeds the threshold value, and then I will have current. If we have current, and this load will be working, and either this guy generates the heat, or if this guy is a lamp, and we will emit lights, or if this guy is a washer, the washer will be working for us, or the driver. You understand, guys? In following circuits, and we will use this the principle to judge and to see and what the condition and how this circuit works. Questions so far? It's called bipolar. So here is a transistor behavior curve. You can see here, okay? So this transition and behavior curve. So here VCE, C is collector, E is emitter. So this is voltage. So this is hypothesized is VCE, the voltage difference between the collector terminal and the emitter terminal. So here is the current going through. And you can see if this one going, if VCE increases at the very beginning, so we almost have a linear. We almost have this linear. This is the change. But after some points, and we will have, and so this one. So this is we will have this very this is a flattening. So you can we have two regions, okay? So linear region characterized by relatively large collector to emitter voltage drops and strong correlation between the base current and the collector current. So this is called linear region. So saturation region characterized by small collector to emitter voltage drops and a distinct lack of obvious relationship between the base current and this is the collector current. And we want to be working in a saturation region, and since we want this VCE drop to be as small as possible. So I will ask you guys, for this one, I will delete this, let you to label what is the linear, what is the saturation, and ideally, which region we should let this guy work in. Why? So we want this guy to be as small as possible. Is that understandable, guys? Because of VCE, if this guy is very high, that means this guy will use a lot of energy. If this guy is very slow, but we have decent current, and then we can the electricity can be used to drive the useful devices. For example, washer, fire, fans. Right? We don't want to have big voltage drop from the for VCE from the collector point, collector terminal, and the emitter terminal. Otherwise, we just just lose a lot of energy. Uselessly, this is voltage is useless. Questions so far? No question? No question. This is the BGT drive. How it drives, how it works, I'm going to tell you. I'll go here, guys. This is 0, this is ground. So this is NPN, right? NPN. If this guy is high enough, and that means the voltage difference between these two terminals exceeds the stress value, and then I have current, then the light will be turned on. If this guy is very low, the light will be turned on. So this is a solid state switch. And for here, so this is PNP. I compare the voltage value of these two terminals. What? How this guy works? If this guy is 10 volts, the fixed. If this guy is very high, if this VIN is very high, that means so the difference between these two guys is very high to the 10 volts. So the difference between these two guys will be very small. And then there is no current. Current equals 0. No current, this guy turn on. However, if I lower this guy a little bit, if I lower this guy VIN, then the current voltage difference between these two terminals can exceed the threshold value, then I will have current. So these two circuits, they work in the opposite way. Okay. For this one, if you increase the VIN, the lamp is turned on. And for this one, if you decrease the VIN, the lamp turn on. Why? Because you are using different transistors. One is NPN, the below one is the PNP. This is a photo transistor. You can see the photo transistor. If we have a light, right? If you have a light, and then you can have this current. So this is the H is the light intensity. H is the light intensity, and this is the VCE. So this is the current. So this is the different light intensity, and you will have with the same VCE, you will have higher the current. And then we talk about the MOSFET. The MOSFET is different, okay? But these charts are very, this is analogous to the chart we have learned. Right? Okay? So keep in mind, so this one, whenever you see the MOSFET, whenever you see the arrow goes in, and so this is N channel. N channel works in the same principle as the NPN. Whenever you see this arrow goes out, so this is a P channel. And P channel works in the same principle as the PNP works. Right? Be very careful. I know this is kind of confusing. And for the NPN, the arrow goes down, going out. But here, MOSFET, and the arrow goes in. And then they have the same working principle. So, we call the metal oxide semiconductor field FET transistor. It's a very long name. It differs from BJT, bipolar junction transistor. It is controlled by voltage, not a current. And when fully on, the conduction path behaves like a small value resistor, not a fixed the voltage drop. So this is the difference between the MOSFET and this BGT. So here characteristic curve for MOSFET, for the MOSFET here, and this is enlarged. So you can see here is a linear. Right? So this for this case, this is the linear, and here is the saturation region. So this is opposite to the BGT. And be careful. Whenever you see something different, and we just memorize the different things between these two guys. So application of BGT, the same thing, right? The same thing. I'm going to show you guys how it works, guys. So for this one, So as I said, for the MOSFET, whenever you see the arrow goes in, so this is the N channel, right? Okay. It's N channel. N channel, it works in the same principle as the NPN. This is how I remember, okay? When I was a student, this is how I remember. It's kind of confusing, but if I remember this way, I can accommodate wrong. So this is looks like NPN, okay, N channel. That means if this guy is high enough, and then we have current, as a result, this light will be turned on. And for this one, so you can see the arrow goes outside from the device. For the MOSFET, whenever it still see this kind of arrow, and we know the P channel, and P channel works in the same principle as the PNP. So it means that we compare these two guys, the voltage. That means if this guy is constant, if this guy is lower enough from the 10, that means this voltage difference will be lower than the threshold, will be higher than threshold value, and then we have current. As a result, this lamp will be turned on. Okay, guys. So for this one, if you want to turn on the lamp, and you need to increase the voltage, input voltage. And for this one, if you want to turn on the lamp, you need to decrease the input voltage. Why? Because you are using different MOSFET. One is N channel, one is P channel. So here is one, and this is NPN and PNP. And how it works, guys? I'm going to talk about these two, and then we have several examples. You can just try to explain this one. Okay, for this one, this is 0. If at the very beginning, if this guy is very low, that means no current. If there is no current, so there is no voltage drop, right? So here will be 5 volts also. 5 volts and 5 volts difference equals 0. The different voltage difference 0 is less than the threshold value, so here is no current either. As a result, this load does not work. Okay? However, if I change this one, increase this one, if I increase this input value, then after this guy voltage difference is higher than the threshold value, I have a current. If I have a current, so here will be on this R3, we will have a voltage drop, right? If we have a voltage drop, if voltage drop is high enough that, so the difference between this point and the 5 volts is higher than the threshold value, and then this one is turned on, so I have current, then this load will be driven. Okay? The same thing here. Now, here is the N channel, this NPN, N channel, so this is a PNP, the same thing. We have other